We continue with the discussion on statistical mechanical ensembles, and we're going to start with the microcanonical ensemble, in which all microstates have the same energy, and therefore they're visited with equal probability. So in this ensemble, we can imagine a system in which there is no matter exchange and no heat exchange with its surroundings. So it's an insulated system. So we have our molecules in the system, and since there is no heat exchange, then the energy of these molecules will remain constant. Now, for discrete systems, we can define the degeneracy as a function of these variables, the number of moles or molecules in the system, the volume, and the energy. Right, so these are the three key variables in the microcanonical ensemble that we keep constant, and these are known. So the degeneracy is giving us the number of microstates with this number of particles, this volume, and this energy. For continuous systems, one can define the density of states in a similar way as the degeneracy, but here this is just this omega dash, and it's really the number of states in a small differential energy, so delta E. So basically this gives us the number of microstates with this number of particles, this volume, and energies between this energy and E plus delta E. Now, for the discrete case, the probability that the system visits a microstate S chi is equal to P chi, which is simply equal to 1 over the degeneracy. So we have to note that the states that are not in the ensemble have probability of 0. So states that do not have this number of particles or they don't have this energy, they have a probability equal to 0. They are not visited by our system, the system that exists in the microcanonical ensemble. Also, for continuous systems, this P chi is replaced by a probability density, and similar equations and similar concepts hold. But of course, to keep our discussion simple, we will focus on the discrete case in which the probability of each microstates is 1 over the degeneracy. So how does this really help us understand the macroscopic world? Well, the microcanonical ensemble enables us to define entropy with respect to the degeneracy. So according to this equation, the entropy of the system is equal to Kb, a constant, times the natural logarithm of the degeneracy. Now, this is a very important equation. This is a major breakthrough in the formulation of the statistical mechanics framework. The equation was formulated by Ludwig Eduard Boltzmann. And of course, this constant takes his name. So this is referred to as the Boltzmann constant or Boltzmann's constant. It has these values in these units. And we have to note that by this definition, the entropy is an extensive quantity. If the system is composed of two independent subsystems, A and B, then I hope you would agree with me that the degeneracy of the large system is going to be equal to the product of the degeneracies of the small subsystems. So this is the degeneracy of the large system expressed as a product. Why? Because if this system can exist in omega A states and this system can exist in omega B states, by a combinatorial argument, the whole system can exist in a number of states which is simply equal to the product of the number of states of A times the number of states of B. We said that these are independent, right? So if these are not interacting with each other, these are independent systems, then this combinatorial argument holds. So if omega AB is the product of omega A times omega B, then if you put this in here, by the properties of the logarithms, you simply have that the entropy of the big system AB is equal to KB times this logarithm, and this logarithm is log omega A plus log omega B. So then you're going to get that the entropy of the large system is simply the sum of the entropies of the subsystems. Our next task is to calculate the temperature in the microcanonical ensemble, and since all of the microstates in this ensemble have the same energy, then of course the internal or thermal energy of the system is also equal to that energy. So U is equal to E. Now remember from our overview of classical thermodynamics that the temperature is equal to the partial derivative of U with respect to S when we keep the volume and the number of particles constant. So in the microcanonical ensemble, we said that S, the entropy, is Kb times log omega. So I can take this Kb, multiply, so take it from here, take it to the other side. So I would have Kb times T equals du d log omega, and then I can just invert the this fraction in the derivative really. So then I can write the following equation. This beta, which is commonly referred to as inverse temperature, which is equal to 1 over kBt, this is equal to d log omega dE when we keep the volume and the number of particles constant. So the temperature can easily be calculated from this equation, provided that we know the degeneracy as a function of the energy, the volume, and the number of particles in the microcanonical ensemble. Now we have to note that for macroscopic systems encountered in nature, beta is positive. This makes sense. After all, you expect temperature to be positive. But of course, we're talking about systems that are macroscopic and for which a classical description is pretty accurate. There are cases, of course, in the quantum world, in which beta can become negative. One famous example for that is population inversion in laser physics. I'm not going to go into the details about this. You're welcome to read about this phenomenon. So you can just search for negative temperatures, quantum systems, population inversion, and read more about this. We can also calculate the pressure in the microcanonical ensemble, noting again that U is equal to E, and therefore the pressure can be written as such. So this again is one equation that we discussed in our overview of classical thermodynamics. So the pressure is minus the partial derivative of the internal energy over the volume, keeping the entropy and the number of particles constant. So how does this really work? Well, if you think about it, for a quantum system, so for example, for a quantum particle in a one-dimensional box, the volume would affect the energy levels. So here is the, in the case of a one-dimensional particle, the volume sort of metric is really the length of the box, and we see that the energy levels are dependent on that length. So if I plot the energy levels and the wave functions for this small box over here, and then if I plot them again for a larger box, I clearly see that the energy levels are different. So then if I have an expression of the energy levels, I can calculate this, which will give me the pressure. So now that we have the entropy from the Boltzmann equation, the pressure from the equation that we just derived, and U, which is equal to E, as well as temperature, which we derived in the previous slide. So with these known, we can calculate any other thermodynamic quantity from the equations, again, that we discussed in the context of our overview of chemical thermodynamics. Let's now move on to the canonical ensemble, which is characterized by a known number of particles, a known volume, and a known temperature. So how do we ensure that the temperature is known? Well, we now put our system in a heat bath. Right? Remember, in the microcanonical ensemble, the system was isolated. There was an insulation here. So here in the canonical ensemble, the system is in thermal equilibrium with a heat bath. So there is heat exchange, but there is no matter exchange. However many particles we put in the beginning, when we prepared the system, this is how many particles we're going to have forever. So this is the number of particles. So the ensemble comprises microstates with fixed volume and number of molecules, and in such a way that their temperature is T. So how does this happen? We said that energy can fluctuate. The system is at thermal equilibrium with a heat bath that is kept at temperature T. And we assume that the heat bath is much, much larger than our system. So if there is a little bit of heat that gets out of the heat bath and goes into the system, still the temperature of the heat bath is stable. So it's going to remain at T. So we would like to know what is the probability that each microstate is visited in this ensemble. To answer this question, we can consider the system of interest, which is in the canonical ensemble, this small system here, as a subsystem of a large system, right? This large system, which is in the microcanonical ensemble and contains our small system and the heat bath. So what we're doing essentially is that we're taking this the heat bath with the small system, we insulate it. In this way, we can treat this composite system as being in the microcanonical ensemble. And we note that due to energy conservation, the total energy of the large system is constant and always equal to the energy of the small system plus the energy of the heat bath. Now, the small system energy, we're going to denote it with E chi, and the energy of the bath will be denoted as EB. Since the large system is in the microcanonical ensemble, its energy remains constant, and what we are plotting here is the energy with respect to a state. So the state of the large system will be denoted as a combination of states of the small system and the bath. So the proper combinations of states of the small system, right? This is the state of our system, the small system, and this is the state of the heat bath. So what kind of combinations are permissible here? Combinations which satisfy this equation. So proper combinations of these microstates, namely combinations with energies that sum up to E, are indeed valid, accessible states of the large system, which is in the microcanonical ensemble. So, as you may have guessed, we are really trying to use what we have learned about the microcanonical ensemble to deduce the probability that our small system will visit state Sx. But in order to formulate an argument, we need to do a few things in order. So the first thing that we need to do is to consider a slightly different partitioning of the states that we just discussed, the states that are accessible to the large system. So here is how I'm introducing this partitioning. And here I'm plotting the energy of our system. Right, so previously I plotted the energy of the total system. Now I'm plotting the energy of our system, namely this small system over here. So here is the partitioning. First of all, I'm looking into states in which the system, right, our small system, is in state S1. So the small system is in state S1, the bath is in state S1b, the small system is in state S1, the bath may be in state S2b. This can be a valid, proper combination as long as the energies of the small and the small system and the bath sum up to E, so that's fine. So this is one class, let's say, of states. Then we go into another class in which our small system is in state S2, the bath, let's say, is in state 47, right, S47b. Again, the small system is in state S2, therefore it has energy E2. The state of the bath is slightly different, but if this state has energy equal to that energy and they sum up to E, everything is fine. So I have a second class of states in which the small system has energy E2 and the overall system has energy E, etc. So I can have several classes of these states, right? And then in general I can have this Sx, Sxi, B, etc. another class. So for a moment we said that we fix the system in some state. So for a moment fix the system in state chi, right, this system. Then the accessible states for the large system are essentially those of the bath, right? So we're fixing the state of the small system. What are the accessible states of the large system? Well, so there is only one state of the small system, and there is a multitude of states for the large, for the bath, and therefore for the large system. So in this case, what we can write is that the degeneracy of the energy level of the bath is equal to the degeneracy of the total energy minus the energy of the small system, E chi, and this is the degeneracy of the accessible states of the large system. Right, and of course this is because the energies have to sum up to E. So you already see that we were able to get an equation for the degeneracy by doing this trick of the partitioning of the states, and now we can apply the arguments that we have learned from the microcanonical ensemble, which will hopefully give us some information about the probability of Sx, the state of the small system here. So we apply the principle of equal weights, and then the probability of this state chi of the system, right? So the probability of the system visiting state S chi is equal to or is proportional to the degeneracy. So the probability for state chi is proportional to the degeneracy of the bath, which is equal to this omega evaluated at the total energy minus the energy of the small system. So the probability of state Sx of the small system, which is in the canonical ensemble, has been found to be proportional to this degeneracy of E minus E chi. Just to summarize the terms that we have discussed, this is the degeneracy of the bath energy level, right, this omega here. This E is the energy of the large system in the microcanonical ensemble, right, so the large system that is shown as insulated here. The large system, of course, contains the bath and the small system. And this E chi is the energy of state chi of the small system, which is in the canonical ensemble. Now, we're going to write this as e to the logarithm of this thing. The reason that we're doing this trick is that this is kind of a nasty function. So we want to introduce a slightly more well-behaved function, which is this logarithm, so that we can continue formulating our argument on the basis of this. Now, the presence of this omega and this E, right, this omega and this E, in this equation is slightly inconvenient. Why? Because this omega pertains to the Bath degeneracy. This E pertains to the energy of the large system. In reality, we don't really care about the Bath or the large system. We really care about this small system here. And of course, you realize that these, right, this omega and this E, are kind of ill-defined. You may have your small system in a small bath, in a larger bath, in an extremely much larger bath, etc. You should find the same results for the probability that your small system will visit state Sx, irrespective of the size of the bath. So we need to do something to get rid of this omega and this energy. And we do this by noting that this E chi is small compared to E, and therefore we can introduce a Taylor expansion for this logarithm of omega, right? This more well-behaved function here. So we can introduce this Taylor expansion. So the Taylor expansion is around E, right? So this is log of omega of E minus Ex. This is equal to log omega E minus E chi times the derivative of the logarithm with respect to the energy. Now, this should look familiar. We recall that the derivative of the logarithm of the degeneracy with respect to energy, of course keeping the volume and the number of particles constant, this is simply equal to inverse temperature. So essentially, this thing here is log omega evaluated at energy E minus E chi times beta, right? So this is the beta here. So we can make then the substitution here, and we see that essentially this probability P chi will be proportional to, and we know that this is essentially constant, so it doesn't matter. So this probability of chi will be proportional to E to the minus beta E chi, right, by doing the substitution of this here. So this is what we just discussed. The probability that our small system will visit state S chi is proportional to E to the minus beta times the energy of that microstate. This is known as the canonical distribution law, or the Boltzmann distribution law, named after Edward Ludwig Boltzmann. And the proportionality constant is determined by the normalization condition. Right, so we said that this is proportional to that. So if we want to find an explicit equation for P chi, then we simply note that the normalization condition must hold. So then if we sum these E to the minus beta E chi over all the possible states, then the sum is this Q here, right? This is the sum, and the probability is equal to 1 over Q times E to the minus beta E chi. This Q is referred to as the canonical partition function. It is a function of n, v, and t, or equivalently n, v, and beta. Right, beta is 1 over kbt. And we note that if the partition function of a system is known, one can derive any thermodynamic quantity for that system just by using the partition function. So as an example of using the partition function to find the thermodynamic quantity, we can consider the internal energy of a system. So we know that U is just the average energy in the canonical ensemble. So this can be written like that. Remember our averaging operations. And the observable in this case is the energy for state chi. This is the probability that state chi will be visited, and this ensemble average is simply a sum over all the states of energy times probability for that state. So the sum, this average essentially, can be written like this. So here I have expanded the probability. The probability is e to the minus beta e chi divided by the partition function, right? So this is the partition function. I have expanded the partition function here. And I note that this is the quantity being averaged, right? And this is the probability of the microstate, as I said. Now, with this being the canonical partition function, I note that this is simply a derivative, right? So this is the derivative of e to the minus beta ex over minus beta. So if you try to do this differentiation, you're going to see that this will give you e to the minus beta ex times ex, right? So we differentiate with respect to minus beta. So this will, this derivative will simply give us what we see here in the numerator, right? Inside the sum. And of course, this is the partition function. So by doing this, then we have simply expressed the internal energy of the system with respect to the partition function and some derivative of the partition function. Why? Because the differentiation and the summation can be interchanged, and now you see that this thing is simply the canonical partition function. So this is now written as d log q d beta, right? This is dq d beta. dq over q is the logarithmic derivative. So this thing is exactly equal to minus d log q d beta with the number of particles and the volume kept constant. So we demonstrated the calculation of the internal energy of the system when the partition function is known, and now we can move on to try to calculate the entropy in the canonical ensemble. Gibbs provided a general equation for entropy, which is actually valid for any ensemble. So this S is equal to minus KB times the sum over all the states. And what are the terms that we're summing? P chi, the probability that we visit that state chi, times the logarithm of that probability. Now, in the microcanonical ensemble, this simplifies to Boltzmann's formula that we discussed in a previous slide of this lecture. So, as your homework, I would like you to prove this statement. And now we're going to talk about the canonical ensemble. So, in the canonical ensemble, we have already expressed the probability that we visit a state, this state chi. So, then we can apply this formula, substituting the probability. So then the entropy is minus kb 1 over q times this sum of e to the minus beta ex, right? This comes from here, times the logarithm, right? The logarithm of this probability. We can break this product, take the logarithms, and this is simply going to be minus beta times e chi minus log q, right? This q over here is in the denominator, so we have a minus sign there. We can continue with this equation that we just talked about. So here I'm just doing the math inside the sum. So the sum of this times this is simply going to give me this term. Then the sum of this times log q. Note that log q is not dependent on chi. So this, right, so sum of this times log q is simply going to give me this sum times log q, and of course with a minus sign. So this sum is simply the partition function, which appears here. So then I can multiply by the partition function. So then the partition function will disappear from here, right? So this is what I have here. And then minus 1 over q times this sum is simply related to the internal energy as we saw before. So that's how this u appears here. And now I'm making the substitution. So beta is 1 over kBt. So in the final equation, I can also multiply by kb, the two terms here in the parentheses. So in the final expression here, I have entropy being equal to U over temperature plus kb times log Q, where Q is the partition function of the canonical ensemble. So if I rearrange, basically I have that Ts is equal to U plus kBt times log Q. Now, if we recall our thermodynamics equation, which relates the Helmholtz free energy with the thermal energy, this is the equation, then we can observe that this thing has or can be related to simply to the Helmholtz free energy. So essentially the Helmholtz free energy is equal to is going to be equal to minus kBt times the logarithm of the canonical partition function. So we have now an expression that allows us to calculate the Helmholtz free energy with respect to the partition function of the canonical ensemble, and also the thermal energy of the system with respect to, again, the partition function. Pressure can also be calculated now that we have the Helmholtz free energy. Again, from the equations of classical thermodynamics, we know that the partial derivative of the Helmholtz free energy with respect to the volume, when we keep the number of particles and the temperature constant, is equal to minus P. So we can simply formulate the pressure as kBt times d log Q dV, right, using the fact that A is equal to minus kT log Q. The volume doesn't appear explicitly in Q, but actually it's there because it affects the energy levels, as we noted earlier in this lecture. So remember the quantum particle in a one-dimensional box. For a small box, we have these energy levels that are quite far from each other. And then if we increase the size of the box, then we have more dense energy levels. So really the volume, well, in this case, this is in one-dimensional box, right? So the metric of the volume is just the length of this square well potential. But of course, similar things apply to two-dimensional and three-dimensional systems. So essentially, the volume affects the energy levels, and therefore it affects Q. Finally, we can discuss the grand canonical ensemble, which is also known as the mu-VT ensemble. This ensemble comprises microstates with fixed volume, right? So here is our small system again, fixed volume, but the number of particles can fluctuate, and also the energy here can fluctuate. So the energy and the number of molecules can both fluctuate, and we know that the system is at thermodynamic equilibrium with a heat bath that is kept at temperature T and a matter reservoir which is kept at chemical potential nu. So here is the heat bath and matter reservoir. They may be two different baths. You know, there can be a bath and a reservoir, or just one bath and matter reservoir, essentially, at the same time. And of course, we make the assumption that the heat bath and the matter reservoir are much, much larger than the system. So if there are a few molecules that go from the matter reservoir into our small system, then the chemical potential of the matter reservoir will still be equal to mu. Similarly, if some heat flows from the heat bath into the system, the temperature of the heat bath will still remain at T. We can use a similar argument as the one we used for the canonical ensemble, and we can prove the following relation. This is the relation giving us the probability in the grand canonical ensemble. So the probability that our system, right, this system here, will visit state Sx is equal to 1 over xi times e to the minus beta times e chi. We have seen this term before in the canonical ensemble, plus beta times mu times n chi. This is the new term that appears in the grand canonical ensemble. And of course, this, as you may have guessed, is the partition function of the grand canonical ensemble, and it's equal to this sum of these terms over here. So xi is the grand canonical partition function. It is a function of the chemical potential, the volume, and the temperature, or equivalently, the chemical potential, the volume, and the inverse temperature. Remember, always beta is equal to 1 over kBt. Now, in the grand canonical and canonical ensembles, the number of particles was fixed, right? Remember, in the microcanonical, this was the NVE ensemble. The canonical ensemble is the NVT. In both cases, the number of particles was fixed, but in the grand canonical ensemble, the number of particles is not fixed. The chemical potential is fixed. So how can we calculate the average number of particles? Well, we can state that the average number of particles is equal to this ensemble average. So 1 over xi times this is simply the probability that the system in the grand canonical ensemble will visit state chi, and n chi is the observable that we are trying to average. Right, so this is again very simply derived from the equation of the general equation for the average that we have seen before. Now we can express this term here as a derivative. So this is the partial derivative of e to the minus of this term anyway, with respect to beta times mu. So this is this here, beta times mu is multiplying n chi. So this partial derivative is simply this term times n chi, which is exactly what we see here. Right, so this is how this came about. And of course, we know that we can again interchange the differentiation with the summation. And if we do that, we're going to immediately recognize this. It's simply the partition function of the grand canonical ensemble. So this whole thing is simply equal to d log xi. Right, we have 1 over xi here, so this would give us the logarithmic derivative. So this is d log xi d beta mu. So this is the average number of particles in the grand canonical ensemble. Let us now try to calculate the entropy from Gibbs's formula. Remember Gibbs's formula. We know p chi in the grand canonical ensemble, so we do the substitutions, and then we find this here. And if we do a little bit of math, we end up with this equation. So the entropy is equal to minus kb times minus logarithm of the grand canonical partition function minus inverse temperature times the average energy plus inverse temperature times chemical potential times the average number of particles. Now, if we recall that the definition of beta, which is 1 over kBt, We can substitute it here and there, and we end up with an expression that looks like this after a little bit of algebra. So this is the macroscopic number of particles. I'm no longer using the bracket notation, right, just for simplicity. And if we recall Euler's theorem, right, in previous lectures, slide 7 of 29a, then we can derive this final equation, which basically relates PV with the grand canonical partition function. So what did we achieve by this? We basically have an expression of some thermodynamic variables again with respect to a partition function, in this case the grand canonical partition function. So let's take a moment to summarize some key messages from these past 3 video lectures, 29a, b, and c. Statistical mechanics is all about deriving expressions for familiar macroscopic thermodynamic variables from microscopic laws. Remember, we want to bridge what is going on in the microscale with what we observe at the macro scale. So in the microscale, we know that some systems, the systems of interest, can be described by Schrödinger's equation or Newton's laws of motion, depending on whether we're interested in a quantal description of nature or a classical description. And the point is to use some statistical arguments instead of trying to solve quadrillions or sextillions of equations, in order to be able to to make statements about the macroscopic thermodynamic laws. There are 2 fundamental postulates in statistical mechanics: the principle of equal weights and the ergodic hypothesis. So the principle of equal weights says that states with the same energy are visited equally frequently, and the ergodic hypothesis states that averages over time are the same as averages over the ensemble, which brings us to the concept of the ensemble. An ensemble, as we said, is a collection of states that the system can visit given some macroscopic constraints. And of course, we said that within the ensemble there is also a probability measure that tells us how frequently a state is being visited. Commonly used ensembles are the microcanonical, in which the macroscopic constraints are in terms of the number of particles, the volume, and the energy. So all of the microstates in the microcanonical ensemble have the same N, V, and E. The canonical ensemble, in which we have microstates with the same number of particles, the same volume, and the same temperature. And the grand canonical ensemble, in which we have the same volume and same chemical potential and temperature. So as a last point, we didn't discuss this that much, but we're going to see some examples that really showcase this. Macroscopically, all ensembles give us the same answers. So irrespective of which one you choose to do your analysis, you should get the same answers, and therefore in some problems it is more convenient to use the microcanonical ensemble, in some other problems the grand canonical, etc. Thermodynamics really, or statistical mechanics, tells us that all of these analyses are correct because all ensembles are going to give us the same answer at the macroscopic limit when we are talking about very large systems.